Hello, this is Daniel Fritz Mathematics with the Professor, and today we're going to be talking about optimization, and we're going to be talking about a maximization problem. And we're going to be talking about, with this maximization problem, how the absolute maximum is applied. So we see that a man wishes to have a garden in the shape of a quadrilateral, which is like this a four-sided figure in this case, in his backyard. He has 50 feet of fencing with which to enclose his garden, and find the dimensions for the largest garden he can have if he uses all of the fencing. Now, as you notice, we always draw a diagram. In this case here, you used to use length here or width or vice versa. In this case, we're going to use X and Y. So we're asking, what is the maximum rectangular or square shaped area that can be closed or enclosed with 50 feet of fencing? And we want to say that can be enclosed. We will say enclosed with 50 feet of fencing. So, step one, let's look at this. We want to let X and Y denote the dimensions in feet, of course, of two adjacent sides of the garden. And let A denote the area of the figure. So this is what we have here, just like over here. And we went on ahead and we drew this again so everyone can see. So step two, we want to show that the area is equal to X times Y in this case. And it's the quantity to be maximized. Now, step three. Since we're talking about enclosing this area, enclosing the garden, this garden. Enclosing, we're going around. So we have to deal with the perimeter of this formation right here, of this here, as we see here, we're dealing with fencing going around this figure. There you go. So when we see that, we're talking about perimeter. Of course, area deals with we're dealing with the inside. But now we're just going to be dealing with the outside here for now. So we're going to look at P is equal to 2 times X plus Y. And we can say 2X plus 2Y feet is the perimeter in this case. As we know, it's the formula for a rectangle. However, since the square is a parallelogram, it could basically take on the same formula for the perimeter of a rectangle, right? Because both have congruent opposite sides. However, but the square has all of its sides are congruent, all the same size. So that square could take on the same formula as the rectangle in the sense right here. It's just that the square, the square can take on the same formula as the rectangle because, of course, X and this Y is basically the same size, or the same dimensions all the way around. Rectangle isn't. This, one side of the rectangle here, its opposite sides are congruent to each other. And of course, its opposite sides are also congruent. Like from here to here is congruent, right? And then of course, this side and this side is congruent. But if it's a square, then we know that all four of these sides are the same. Now, with that just said, I just wanted to clarify that because we don't know if it's a rectangle or we don't know if it's a square based on how much fencing has to be put around this area here. Now, let's continue to look at step 3 though. Even though we have the perimeter equal to 2x plus 2y, we have to, since we're looking at 50 feet of fencing, then we need to substitute P, which equals to what in this case? We're saying P is going to equal to 50 feet. So now it'll be 2x plus 2y is equal to 50. So next, let's solve the equation for y in terms of x. And so we say 2x plus 2y is equal to 50. So we take negative 2x to both sides. And we see that 2y is equal to what? Negative 2x plus 50. And we want to what? Solve for y. So we're going to divide 2 to both sides. And we come up with y is equal to negative x plus 25. Now, looking at this, we can substitute y into x is equal, area, or a is equal to x times y. So since this is y here, we want to take negative x plus 25 and plug it in there for y, just like this. So x times negative x plus 25. So the area is going to equal to negative what? When we distribute, right? When we distribute x to each of the terms, we come up with area is equal to negative x squared plus what? 25x. Now, remember the function to be optimized must involve just one variable. And since the size of the quadrilateral must be non-negative, meaning it can't be a negative number, that is, we must have this relationship, x is greater than or equal to what? 0. And we say that the expression y is equal to what? 25 minus x. That has to be greater than or equal to 0. Now that is, if we can rewrite this expression, we can say that 0 is less than or equal to x, less than or equal to what? 25. Now, after we solve for y, when we solve for y and get this relationship, we basically can get our boundary conditions and endpoints and our intervals based on rewriting this as such so that the problem can be optimized, right, and solved. So thus, the problem is reduced to finding the absolute maximum. Now we're looking at the absolute maximum. So area is going to equal to the function that is, which is equal to negative x squared plus 25x on the what? Closed interval from what? 0 to 25. Which again, this is inclusive because this has brackets around. So we're going to use 0 and 25 when we calculate the absolute maximum of the area. However, we still have to find the derivative and find the critical points, right? So again, step 4, we find the absolute maximum of the function, right, on the interval from 0 to 25. Just like we did in the previous videos when we did the absolute minimum and absolute maximum problem. So we take the derivative of this function, negative x squared plus 25x, so we come up with negative 2x plus 25. And so we, again, what do? We set the derivative, the first derivative, equal to 0, and then we solve for what? We solve for x. So when we solve for x, we come up with 12.5, which we come up with clearly one of the sides. X is equal to what? 12.5 feet. Now, so since that is within this interval here, it'll qualify to be continued to be involved or solved, or can we say we can plug this value into the problem. So this problem or this value can be used to help solve the absolute maximum of this problem. If it was anything different but outside these intervals, outside of 0 and outside of 25, like you've seen in one of the problems we did in the previous video, then we couldn't use that. That number would be thrown out and would not be used or be considered used in this problem. So since 12.5 is within the interval, we can use that to substitute in to solve and find out what the maximum area is. So when we do that, we're going to use, again, this is inclusive, so we're going to use 0. When we plug 0 in to the original function, we come up with 0. And then if we come up here and we use what? 25, we're going to come up with 0 when we plug it into the original function, 25 in the original function. But guess what we do is Substitute 12.5, since it's one of the critical points, right? If we plug this in, guess what we get? We get a maximum area of 160.25 square feet, because we got to know the area, right, of that, right? So with the absolute maximum being 156.25 square feet, right, we see that the size, the dimensions of the size are 12.5 feet. So here we have 50 feet of fencing, going around an area of 156.25 square feet. So this is how we solve a problem dealing with maximization. So stay tuned for later videos, and also stay tuned and always watch the professor.